Well, it's a great pleasure to be invited, and it's actually lovely to see you all again virtually. So I'm going to start off with an apology. My talk is not really about data analysis or trying to characterize neuronal dynamics. It's more standing back and asking whether we can understand neuronal dynamics as using entropy or notions of entropy, relative entropy and energy as the objective function itself. So I'm going to talk about the brain as doing inference and trying to cast that inference in terms of thermodynamics and information theory. So as such, this can be taken as a light entertainment. It's not going to address some of the hardcore issues that you've been wrestling with. I had just one message with this talk. It was, given I only have 20 minutes, and I was just going to talk about sentient behavior with the emphasis on behavior and the imperatives for action when looked at from through the lens of the brain as an inference machine. However, I've been so compelled and intrigued by all the really interesting sort of concept and issues that you've been talking about for the past couple of days. I'm going to go through my slides, the first set of my slides, quite slowly, just to try and use them as placeholders to revisit some of the sort of key ideas that you've been discussing. And as such, I'm unlikely to get to the end of the talk, but that doesn't matter. So Jennifer, can you stop me when my time is up? And it doesn't matter, because I think most of the interesting stuff I think will be in the discussion. So what I want to do is address the teleology of the brain from the point of view of energy and entropy, and ask the question, what is the brain in the game of doing? And we already know the answer to that. So Elaine told us that, basically it has to comply, as with all things, with James's maximum entropy principle. Elaine reminded us that one way of looking at that is to minimize surprise. So the story on offer here is essentially neuronal dynamics can be understood as minimizing surprise under the maximum entropy principle. And that's about it. I repeat that the additional focus I was going to bring to the table was, what does that mean for choosing what to do next in order to comply with those imperatives? And I was going to talk about that in terms of self-evidencing, normative models of what it is to be a sentient creature interrogating our world and making sense of that world, the implications or the benefits of applying surprise minimizing, entropy maximizing principles for artificial intelligence, and then briefly rehearse how we apply those principles in computational neuroscience in terms of belief propagation and epistemic foraging. So I'm going to basically start by assuming that everything that we do and our neurons do, and everything that characterizes us over different timescales can be understood as maximizing the probability of the outcomes given me or M or a model of the world. So basically just the likelihood of our observed sensations. And just to put this in a larger context, this, if you like, this quantity, this probability of outcomes given me, can be read in many different ways, which provides a nice perspective on different sort of global theories or attempts to understand or formalize or provide normative theories of behavior. So I can read these outcomes as characteristic of me, so that they're the kinds of outcomes that I would expect to encounter. And if I act in a way or selectively sample those outcomes, then I'm effectively maximizing the value of those outcomes, because they are defined as the most likely kinds of outcomes that I would want to sample. And if we treat that that quantity, that log likelihood, log marginal likelihood, marginalizing over all the causes, as a value function, then we can understand this optimization, or this normative perspective in terms of reinforcement learning, optimal control theory, expected utility theory in economics, and so on. We were asked previously, what is surprise? Well, in my world, surprise is just the negative value, or the negative marginal likelihood. It's provided or equipped with an evidence lower bound, negative physical or physics-free energy, which we'll talk about in a second. But simply, surprise is a negative value. It's the negative or the implausibility of an outcome given me. And from that, we can read surprise as surprisal, or self-information in information theory. And we can interpret this in terms of the Informax principle. We've seen Linska referred to, minimum redundancy, Horace Barlow, and indeed the free energy principle. Clearly, the time average of surprise is entropy. So if we're trying to maximize value or minimize surprise, we are effectively trying to resist the second law. We're trying to minimize the dispersion of our states, or the outcomes that we are exposed to. And this, of course, is the holy grail of self-organization, synergetics. And if I were a physiologist, it would just be a statement of homeostasis, trying to keep my interoceptive outcomes, my interoception, within plausible and physiological bounds. I'm going to read this marginal likelihood, though, in another way, which would make sense to a statistician. It's just, and I'm going to do that and license that interpretation by replacing me with a model. So it's a probability of some observables, outcomes, given a model of how those outcomes were generated. And on that reading, this becomes a model evidence, and then we can spin off from that the Bayesian brain hypothesis, evidence accumulation, and things like predictive coding. So that's setting the scene. A focus of what follows is really this formulation or bound in machine learning known as an evidence lower bound on surprise, or the log marginal likelihood. So this is where we get to the maximum entropy principle under those prior constraints. So the reason it's called a free energy is it can be decomposed into an energy and an entropy, and we're going to be working with a negative free energy here. So we're talking about a negative energy and an entropy, where I'm reading an energy or a potential as a log probability, or a negative log probability. And I've written out the free energy in this form just to emphasize what we're talking about here is indeed the maximum entropy principle here. So this is just the entropy of some beliefs Q about states of the world generating my observations at any particular time tau here. So if I want to maximize F, I'm going to want to maximize my entropy, whilst at the same time maximizing the likelihood of the observation. So I'm doing maximum likelihood basically under the maximum entropy principle, subject to prior constraints, my prior beliefs about states of affairs out there generating the observations sampled by my sensory epithelia. So that's the basic construct. I'm going to now unpack what that means and how one can understand the imperative to self-evidence, or maximize model evidence, or minimize surprise using this particular formulation or formalism for the maximum entropy principle. The first thing I'm going to do is just motivate why this might be a good way of describing behavior and intelligence from a number of perspectives, particularly sort of data analysis and artificial intelligence, and indeed data mining. What I've done here, I've just rearranged these terms to explain why this quantity is known as an evidence lower bound in machine learning and artificial intelligence. So just by swapping around the terms, what I can do is express this in terms of an expected probability, log probability of the outcomes here. Notice that this does not entail the states generated as outcomes. I can just focus on the log probability, the evidence itself, the model evidence, minus a bound, a KL bound, or relative entropy here, which is just the difference between the true posterior of over the states or the things, the causes of my observable consequences, and my posterior beliefs queue about those causes. And because this can be never be less than zero, this is why it's called an evidence lower bound. It's always less than the log evidence. So if I maximize f, I'm implicitly maximizing that log marginal likelihood or minimizing that surprise. So that's a perspective on this sort of optimization process that is used to promote the use of this variational inference or bound inference to provide explainable AI, in the sense that what we have in this expression is a recourse to a probabilistic relationship between causes and consequences known as a generative model. So the probability distribution over the joint causes and consequences, the hidden causes that we have to infer, and the observable outcomes or consequences of those causes. And so the beauty of this approach is it rests upon explicit generative models. You have to write this down before you can define this quantity, before you can optimize it. It entails a precise specification of prior assumptions and all the hyperparameters if you have a hierarchical generative model. It leads to a design optimality, whether it's experimental design or designing an artifact or designing your steps in your optimization scheme. And as we'll see later, it leads to literally optimal Bayesian experimental design, sometimes known as active learning, abductive inference, that can be in some instances autodidactic. The other aspect of this is, because you are effectively, or we will see that you are effectively, when you put action into the game, sampling those data that provide the best kind of evidence for your model or you now have a principled way to address data foraging and epistemics, choosing the right neurons to record from, or choosing the right Wikipedia page or news channel to resolve your uncertainty about the world. Just rearranging these terms again to provide another perspective on this free energy bound. So what I've done here, I've just swapped around the terms again. It's still an evidence lower bound, but this time it's expressed in terms of accuracy and complexity. So maximizing the free energy here maximizes the accuracy, the expected log likelihood of outcomes given their causes. And this quantity here, which is the relative entropy or the KL divergence between the posterior and your prior. And this is, I think, a really nice term, and I think implicitly has been discussed a lot yesterday and today. So, for example, one could construe the synaptic homeostasis that Chiara was talking about, that sort of housekeeping that improves generalization and learnability, enhancing performance, say, accuracy, the following day. One can construe this basically as minimizing the complexity, removing redundant degrees of freedom in your generative model of the world, literally by taking out those unstable, friable synaptic connections and associations in a judicious way that minimizes complexity without compromising the accuracy. And clearly, to focus on the complexity part here, we can ignore the accuracy simply by switching off observations, by sequestering ourselves from the sensorium whilst asleep and letting those slow wave dynamics roll forth with abandon. From a sort of statistical perspective, this minimization of complexity that could also be read as an algorithmic complexity, and I notice there's several references to the data compression or compressibility perspective on this. This complexity, if you like, is the placeholder for that. The fewer bits that you use in order to make sense of a message or to explain some data, then the more compressed it is and the more compressible it is. And this, of course, is just an expression of Occam's principle that in the brain would be revealed in terms of functional specialization and redundancy, minimization, and efficient coding. So Jennifer was mentioning before degeneracy and redundancy from Jerry Adelman. When we revisit the distinction between degeneracy and complexity, redundancy in this form of formalism, then you sort of associate redundancy with complexity. So redundancy is a bad thing, and yet you have to pay that price, that complexity cost, in order to provide an accurate account of the data. So there's always redundancy there, but you're trying to minimize it. And that sort of contrasts with the notion of degeneracy, which I think is most simply read in terms of maximizing the entropy so that you don't commit to a very particular way of explaining some data or ways of doing things. So other ways of understanding the imperative to minimize complexity that may be afforded by things like synaptic homeostasis is that you're minimizing the computational cost. So this just scores the degree to which you've changed your mind in the face of new data. And if you can do that with as few bits or parameters or degrees of freedom as possible, then you're minimizing your computational cost. And you can read this now as a kind of bounded rationality, and choosing the right mean field approximations leads you to approximate Bayesian inference. And that can be understood in terms of structural priors on the way that you try to explain your particular world or the way that it is sampled. We've already heard about Landauer's principle, the energy required to erase bits. I find the Jasinski equality probably more relevant in this setting because it applies to open systems that are far from equilibrium, provided you sort of do your updating sufficiently slowly. And what it's saying is that there is a thermodynamic homologue of the computational cost. So put this very simply, if you've got the best kind of computer for doing any accurate explanation of any data, then that computer should use the least amount of electricity and be as small and as compact and as cool as possible, as indeed the brain is if you compare it to some of the supercomputers around nowadays. So the story I did want to tell, and we're not going to have time to finish this, is what does this imperative to maximize accuracy whilst minimizing complexity mean for the moves that we make on the world in terms of securing the next round of data, whether we're whisking or whether we're making a saccadic eye movement or whether we're attending to the next phoneme. What are the best actions or plans that would secure the right kind of data to maximize this quantity? And the story would have been of the sort that effectively maximizing the expected accuracy given an action or given a plan or a move translates in terms of optimum Bayesian design and active learning, whilst optimizing the complexity or minimizing the expected complexity effectively is the same as making Bayes optimal decisions by minimizing risk. So we've got two, if you like, aspects to self-evidencing, minimizing expected surprise, that can be unpacked in terms of optimally designing experiments, perceptual experiments that tell us where to look next, whilst at the same time minimizing the risk of the outcome of making that move or looking over there. And I would normally take you through this with a series of questions. Starting off by asking, if you're an owl and you're hungry, what are you going to do? And normally people reply, I'm going to look for food. And in so doing, highlight, I think, an important dichotomy between different ways of formalizing or writing down normative models. And that dichotomy rests upon the notion that there exists some value functions of states of the world that would ensue if I made that move or did that control U to produce these new states of the world. And if I can write down that value function, I can always identify the optimal sequence of actions or action from any given state to secure the most valuable state. But the answer before, I'm going to search for food, tells you that you're effectively making moves to resolve uncertainty, in this instance about where your food is. And the key observation about that is its uncertainty. The uncertainty is an attribute of your beliefs about states of the world, not the actual states of the world. And so we have to replace this value function with a functional or a function of a function, in this instance, a function of beliefs about states of the world. So the real question is, what would my beliefs about states of the world in the future be if I made this move? And furthermore, it matters whether I seek and search for my food and then eat it, or try to eat it and then search for it. So we have a slightly different perspective known as sequential policy optimization, where we're now trying to optimize, maximize an energy function of beliefs about the world, leading to effectively a description of good actions that are trying to extremize a path integral of an energy function of beliefs that in fact is just a statement of Hamilton's principle of stationary action. So normally we'd contrast the Bellman optimality principle, which predicates itself upon the existence of a value function of states of the world, against a Hamiltonian principle of stationary action, which is more apt for describing behaviors that optimize beliefs, Bayesian beliefs, subpersonal beliefs about the world. And then we would have looked at the anatomy of active inference under that lens, where basically that goodness function, that functional is that expected free energy that we were referring to before, essentially comprising the accuracy and the complexity that constitute this evidence lower bound, but lifted to the future, where now we are evaluating complexity and accuracy in terms of the expected complexity and accuracy in the future, given a particular plan. And we will talk about that in terms of risk and ambiguity. And I'm sure I'm out of time now, aren't I?
I think you can have another 2.5 minutes by my clock.
I will use that 2.5 minutes to show you what you would have seen had I not got distracted by human degeneracy and surprise and all those wonderful concepts. So what I would have done is take you through that sort of different ways of writing down this, to my mind, a sort of machine learning version of James's maximum entropy principle, and explain them from the perspective of different people. For example, Bayesian surprise in visual search, or Informax principles, or minimum efficiency maximization from the point of view of Horace Barlow, how that relates to KL control and risk sensitive control in engineering and economics respectively, and how very special cases emerge as expected utility theory when we take uncertainty off the table. I would rehearse the notion that optimizing expected free energies is basically securing the maximum expected value and information gain as a function of your plan. And I've shown you what that looks like when you apply off-the-shelf variational message passing Bayesian schemes to generative models, and how to use a Markov decision process, and taking you through the, well, although it does look like it, a simple model of a world generating your data, and then just noting that the remarkable formal similarity between these Bayesian belief updates under this imperative to maximize free energy and its expected value in the future. The remarkable isomorphism between the kinds of equations that we use in computational neuroscience in terms of perception and belief updating neural dynamics and learning and assistive plasticity, and indeed action selection. I'm going to give you a little worked example with a mouse searching for a little red ball, exploring initially and then being compelled to exploit when it got bored because there's no more information gain, and closed with a key link, which I would have spent hours talking about, relating this fundamental or first principle account of good behavior to thermodynamics via integral fluctuation theorems. And then I would have closed by noting that evidence simply is simplicity plus accuracy. I would have then thanked all the people whose ideas I've been talking about, and then thanked you for your attention. Thank you very much.